Hello again, and welcome to my object detection series. Today we will talk about SWIN transformer. In the previous video we talked about VIT transformer. This one is quite similar in terms of how it's used, the scale and all of that, but slightly different in terms of the actual model architecture. So this is the plan for today. So we'll talk about motivation. So what problems we're trying to solve, why do we think the architecture will work well. Then we'll talk about the actual architecture of the model. So the hierarchical patches structure, the shifted window attention, and the relative positional bias. Then we'll again look at how it all worked out and what is the philosophical differences to the previous model VIT, and we will look at results. So let's start with the motivation behind this, and I call this the image tokenization problem. To be able to use transformers, we first need to represent our input as a sequence of tokens, where each token is basically an embedding vector. So we can do that in text by using tokenization. So for example, we can take a sentence and split it into words, and we call each word a token, and then perform some sort of embedding lookup to match every unique word to an embedding vector and to train that. It's not ideal to tokenize text by words. There are better ways to do that, but it works quite nicely as a starting point. So for example, European, economic, all of those are words and they have some atomic meaning behind them. And so it's useful to have them as tokens. It will not be ideal because you might think about word parts like Europe, and that Europe is a part of European as a word. So there are actually better ways to tokenize text, but this lecture is not about text, so let's go forward. We could instead tokenize just by letters. And in some cases, that actually does give you more flexibility in terms of what your model can generate, for example. But it will have two problems. So problem number one is that now letters are not as expressive. So if you think about how the transformer will actually look at this data, the transformer will compute all the pairwise attentions. And so when we tokenize by words, the pair of words economic area, for example, is really meaningful, right? So economic area is a good pair of words to understand the meaning of the sentence. On the contrary, if we just look at letters, so for example, T and U, or O and M, it's much harder to assign some atomic meaning to that. So it's just too small of a piece to have some meaning on its own, meaning that it will take a few layers just to look at individual letters, combine them into words, and then those words will find meaning. So that's the first problem. So we don't have that much meaning in this elementary particles letters. And the second problem is obviously the cost. So transformer complexity scales quadratically with the sequence length, which means that if we opt for tokenization by just letters, it will just be much more expensive and slower to actually perform anything useful on top of this letter separated text. Now let's come back to images. And so before we apply transformers, and this is what we want, this is what we wanted in the VIT transformer, this is what we want in SWIN transformer, we believe that transformers are the better architecture as long as we manage to create the proper input for transformers. So in images, that's not really obvious. So we can once again just look at the smallest elementary particles, in our case pixels, and just try to pass that into the transformer. And here we'll have the same problem we had with tokenizing texts by letters. First of all, each particular pixel having certain color does not really represent a lot of meaning. Meaning only arises when you combine a lot of pixels together. So that's the first problem. It will take a lot of transformation. It will take a lot of layers to even combine these pixels into something that might have meaning. Second problem is that there is just too many of them, and it's much more complex problem than in text because there are much more pixels in a typical picture. And so we just can't afford to do that. Alternatively, we can split the image into patches and just consider a patch as this unique token. So it is a similar approach to how we did with text in terms of like the scale of it at least. So we basically unite several pixels into patches, and then we consider a patch this elementary token input to the transformer. And this is how it actually done in VIT. So, and this is plotted at scale. So this is the actual patch map for VIT transformer. So it works better. So we now have some meaning behind a small patch within the picture. And also there's a limited amount of them, so we can actually afford to perform our transformer and self-attention. However, it is still not ideal. So if we look at this particular patch to the right here, first of all, there is a human somewhere there, right? And we can see that half of the human is in the upper patch, and then the other half is in the lower patch. And so it's not really obvious like how it should be. Should the entire person be in the same patch? That will allow the dense layer that is projecting this patch to some embedding to understand that it's a human, but then it will not use any pairwise cross interactions between different parts of the image. On the other hand, if we split the person in two, now the upper patch will actually communicate and compute attention with the lower patch. And so we might get some extra signal from looking at two halves of the person and trying to understand them, how they interact. But it's still not obvious, not ideal. In addition, if we actually wanted to solve a different task like image segmentation, where we actually need to say which precise pixel belongs to the person and which doesn't, then it will be just impossible because our resolution is not enough to have that fine-grained details of the pixels, basically. And so this is the problem the SWIN tries to solve. So it tries to redefine how we split the image into patches, how we pass that to the transformer, such that we can at least afford to compute some transformations on top of higher resolution images, which is especially useful if we want this detailed output of pixel segmentation, for example. I want to admit that I still believe that the problem is not solved. There is no elegant solution like we had with text, where you'd have atomic words that have some meaning behind them. It is still not as elegant as this, but at least it works better for real-life cases. Now let's talk about the hierarchical patches architecture. So we start with an image and we divide it into a certain number of patches. And we want to keep the number of patches high enough so that the actual patch is small at the very beginning, at least, and it is able to capture the fine detailed information, which is really important for pixel segmentation. Then we basically flatten that out, pass that through our attention layers, get some output, which will be in the same shape. So I'll just represent it as the same image. And then at some point, we merge the patches. And so we transform the initial image somehow using our self-attention layers. And then we merged, let's say, every 4 patches into one. So 2 by 2 square into one patch. So now we have a more refined image representation with a smaller number of patches. And we just repeat the operation. So again, we pass that through several self-attention layers. Then we merge the patches, get even less of them, which allows us to basically continue computing attention cheaper, and so on until we arrive at something with just a few of them. So how exactly this patch merging operation works? So let's say we are currently at 16 by 16 resolution. So we select 2 by 2 square, and we do that for every part of the image. And that's basically like 4 patches, each of them represents some part of the image. Then we just concatenate all of them together, meaning that we arrive at one patch, but now the embedding dimension of each of the 4 initial patches got concatenated together, and that yields 4x the initial hidden dimension. And this is how you can represent just basically pieces of image processed into embedding and then stacked together. And then we pass that through a dense layer to project this 4x hidden dimension down to 2x hidden dimension. And so this works similar to how we've seen that in CNNs like ResNet. So on each step on this merging stage, we reduce the resolution and we increase the hidden dimension. Okay, now let's talk about shifted windows attention. So first of all, this is the representation of just the window attention. And so what we are doing here is we have our input consisting of image divided into patches. And then on top of that, we also define a window, say 4x4 patches. And here it's represented in red. We compute what is called window attention, where instead of every element, every patch on the image communicating with every other patch, which yields quadratic complexity and all pairwise interactions between patches, instead we limit this self-attention only to patches within the same window. So this guy can communicate here, but not to the neighboring windows. And same goes for this one. So a patch within this window will only be able to interact with neighboring patches in this window. And so we need that because in the hierarchical patches architecture, even though we have this decreasing amount of patches on every stage, the first one, if we want to make it really high resolution, it is still going to be enormously big, and we wouldn't be able to afford to compute full pairwise attention for every patch. In this architecture, since we limit the effective distance of this pairwise communication, the complexity is actually linear now, because we fixed the quadratic complexity to fixed window size, and now it scales linearly with the image size. On top of that, we perform this computation layer by layer, and every second layer we shift our windows half period to the right and down. So if the first window was here, now the next one shifted a little bit to the right and down, and we do that for every window. And that basically solves two problems. So first of all, if we had this person who somehow got in the middle of the window, so half the person is in one window and another half of the person is in another window, then this shifting will solve the problem, because now on the shifted window, the person will definitely just be in one window and the attention will be properly computed. In addition, this now acts similar to how convolutions do. So instead of having this one area in where we have all the pairwise interactions and information flowing, the area effectively expands after every layer. So we've started with just this window, 4x4 in the upper left corner, and we consider that information has spread out across this window. And then after the shift, the same information will flow half a window size outwards. And so if you continue the process, it will keep flowing and flowing and flowing, effectively allowing the logic of the neural network to cover more and more area. Then we do the patch merge operation in decreasing the number of patches, and we keep this window attention size the same. So because we now have less patches, this window now covers bigger portion of the picture. And so we continue the process. So we shift this window, this bigger window again, perform computation again. Then we do another patch merge. At this point, the window attention already covers everything. So by this point, it will act exactly the same as just the normal full pairwise self-attention. So again, this is how it will go. We start with the first image divided into patches, let's say 16 by 16 patches, 4x4 attention window. Then on the first layer, we just apply the window as is. On layer 2, we shift the window by 2 patches to the right and down. And again, compute this window attention. Layer 3, the window is back to normal, and we compute the window attention again. Layer 4, again, we shift the window by 2 patches, and so on. Then we perform patch merge operation, turning our 16 by 16 patches into 8 by 8, but the attention window size stays the same. Then we continue the same process, so we perform window with attention, then shift the window, perform it again, shift it back, perform it again. Then we do the same for stage 3, and so on. And so this is why we're doing this. So now the complexity of the model scales linearly with the image size, because we've limited the number of interactions to only pairwise interactions within the window. And this is the primary fact that allows us to pass in higher resolution patches as an input. And so the actual SWIN transformer uses 56 by 56. So it's like 4 by 4 pixels patch. So it's quite enough resolution to perform this high detail tasks like pixel segmentation. And this is also why we had this weird hierarchical stage structure, because now we basically do similar thing to convolutions. So we start with the really high resolution images, and now the actual computation of attention is limited to a local area. And then we perform some transformations, arrive at more refined representation of the image. Then we downscale it to smaller resolution and effectively increase the covering area of our pairwise computation. So now, instead of computing attention in a small area, we compute the attention over the bigger area, and so on. And after every stage, the number of patches goes down, and the effective size of the area that we cover increases. And so, thanks to this, we managed to effectively have both small scale processing that is really good for fine detail attention, and really big scale attention that looks over the entire image and can argue about different parts of it interacting together. And we hope all of that with linear complexity. Now let's talk about relative position bias. So let's say we are computing our window of attention. So we have our 4 by 4 window with patches, and we want to compute our self-attention within that window. So always when we deal with transformers, we need to have a flattened sequence. So when we deal with images, we always flatten the image out. But then once we do that, we lose the actual positional information about where every patch was located. And different models deal with that differently. So for example, data-like models just have what we call absolute embedding, positional embedding, where every patch will have a unique embedding corresponding to its coordinate added to that token as an input. So if we have 4 by 4 window, that's 16 different patches. And so we initialize 16 different embeddings and just add to that. And usually this absolute coordinate depends on the coordinate within the image. In our case, we want something different. First of all, because of the whole hierarchical shifted window thingy. Now, the same window will shift around. And so we're not that interested in the absolute position, but rather the relative position. So when this patch communicates to this patch, for example, we don't want to know that this patch has coordinates 0, 0, and this one has 2, 2. Instead, we want to know that this second patch is 2 to the right and 2 down with respect to the first one. So this is what we do. We provide the model with the relative position bias. And so the problem is now that we need basically much more unique parameters to represent that. Because if we're talking about just the absolute position, that was relative to the total number of patches. So if we have 16 patches, then we need 16 different embeddings. Now we want relative position between every pair. So that's now 16 squared, or 256 embedding. It's actually a little bit smaller than that, because, for example, these two patches, their relative coordinate is the same as these two. So it's also 2 to the right and 2 down. So basically, out of 256 unique positional combination, only 36 of them will actually differ. So, and this is how it actually looks like in code. So we initialize this 36 parameter matrix, and then we look up the embeddings for every pair that we need. Another difference is how we then use this positional bias. So if with absolute embedding, we had the embedding, we had the token, we added them up before passing to the self-attention layer. Now we do that somewhere in the middle. So we have our tokens, we compute pairwise dot product to arrive at attention matrix. And attention matrix already tells us the interaction between two positions, basically. And then we add this parameter to the attention. So if we had this token here, we compute a dot product between them to arrive at attention weight. And then we add this position bias to the attention weight. So this changes how we do the computation. And finally, another difference to the classical positional embedding is that we can now do that at every layer. So if in VIT, in Debtor, we only initialize positional embedding once at the very beginning and then just add it to the input, and then layer after layer after layer, we're not adding any extra positional information. Here we have a different positional bias matrix for every layer. So after the first layer, in the middle of the first layer, we have the first set of positional biases. For the second layer, we have the second set, and all of them are trainable. So this is another major difference. Finally, let's discuss the results. So the SWIN model is basically the same as VIT. So it has the same concept of taking an image, dividing it into patches, and then applying self-attention on top of that. The only difference is in how exactly that is done. So SWIN transformer reduces the effective distance of this attention calculation, thus making it computationally more feasible. And to compensate for that, uses the hierarchical merging of patches to arrive at low resolution but higher scale representation. That turned out to be successful. So, for example, on Coco dataset, just using this bare model to do object detection, we can improve previous state of the art by 2.7 multi-average precision. But typically nowadays in 2024, it is more often used as a backbone, replacing the more lightweight ResNet, for example. And an example of such model can be DINO, that takes a backbone, either ResNet or SWIN transformer, and then a detection head that are based. And that one is basically really, really effective in object detection. And it was state of the art for quite some time. It scales better with the input resolution. So we can increase the resolution of the input image and only incur linear complexity costs as opposed to quadratic for a typical transformer or VIT. It also makes it suitable for dense prediction tasks like pixel segmentation. When you need prediction for each specific pixel in the image, you need high resolution to be processed by your model. However, if we compare that to VIT, so one of the philosophical principles of VIT was that we want to remove inductive bias that we've added to our models. So we talked a lot about that on one of my previous videos about VIT. So, and this is also what the authors of VIT talk about in the paper. So CNNs are effective because they have this inductive bias embedded into the architecture itself that says that we need locality, meaning that to understand what it is, we need to look at the neighboring areas, and we need translational symmetry. So the philosophy behind VIT was that let's not do that. Let's instead have some generic architecture based on transformers and just a lot of data. And then hopefully the model will learn useful things on its own. So it will learn locality if it indeed needs locality, But then in some cases, locality might actually be counterproductive. And so in these cases, the model will behave differently. However, now we realize that it doesn't work as well, at least from the computational efficiency standpoint. So although we can learn the same principles just from data, if applying these principles is still computationally ineffective, that basically makes such a model unusable. And SWIN basically brings all of the same inductive biases back. So it brings back the locality in the way it handles the window detention, focusing on a small area within the picture. It brings back the translation symmetry in how it encodes the positional bias, in how it shifts the windows. So it brings all of that back and basically makes the model more effective because of that. But probably we'll lose something there too. So it's still an open question. But we do know that SWIN transformer is better on majority of the tasks as compared to VIT. Finally, let's talk about what will come next. So I have a channel. On this channel, I've been focusing on computer vision and lately object detection. So today we talked about SWIN transformer. The very next video will be about reading SWIN transformer source code, which might answer some question you might have about how it actually works. I also have videos about VIT, another big transformer used for image recognition, and a whole series of other object detection models, starting from YOLO, which is an old school CNN-based model, which is quite lightweight, quite fast, and because of that, it's still popular. And then the DETR family of models, which basically proposed a new approach that might be fundamentally better and lighter than what we've seen before with YOLO or regional proposal networks. And then a lot of improvements on top of that to actually make it work. So deformable DETR, DAB DETR, denoising DETR. And then all of that basically brings us up to a model that used to be state-of-the-art for quite some time called DINO, which combines everything we've talked about before. So it combines all the DETR-like models, it combines the SWIN backbone, and it is a really good model. And then finally, by the end of 2023, a new model came out that is even better than DINO on object detection, and it's called CoDETR, and also hope to talk about it soon. So we have a lot to cover. See you soon.